concepts about distributions for the discrete and continuous random variables, I wanted to show you some applications of the stuff that we've been learning in this class so far. So the idea is to give you understanding of how these concepts are used and why are they important. So what I'm going to do is to show you a simulation model. Actually, this is an animated simulation model, and I'm going to start with a very simple model. Let's see if I can zoom right here. Okay, so this is a software that is called Arena. Rockwell Software develops this software, and this is a model of an assembly line. So as you can see in this animation, we have 4 operators, and we're going to have some parts arriving to each station. Each operator is going to do some work on the part, and then it's going to move that part to the next station. So first, let me run this so you can see some of the things that you can notice from this model. Again, it's a very simple model. Is that we have some performance measures like total production time, the working process, and the average cycle time of each part. And we also have a clock here that shows the time of the simulation. So if we run this, you see how the parts are going to start moving, and basically the animation shows that when the color of the operator turns to red, that means that the operator is busy. There will be some overlapping on the boxes, but the idea is that you can see that at any time in the process, these operators are busy and idle. So you can see the different states, and you can see by the time of day the number of production items, and the working process, which is how many items do you have in the line, and the average cycle time for completing a particular part. Now, how does this relate to the material that we are learning? Okay, so to build these models, you need some probability models to input. So specifically for Arena, let's say you see those arrivals, the inter-arrival times for those boxes are coming from a probability distribution. So the way you construct this probability distribution is that someone has to go to the actual system. It will stop there with a clock, and it's going to start recording every time a unit arrives to the process line. So once you get that, then you can do something like this. So let's say we define our random variable to be the inter-arrival times of those boxes. And from this person who is collecting the data from this system, he came up with this table. So the first arrival, first part arrived at time 0, second part arrived at time 25.98, and so on. So you have the times for each arrival until part 23. Okay? But your random variable is not the time of the arrival, your random variable is the inter-arrival time, which means that you want to know how much takes to go from one part to the other. What is the inter-arrival? What is the time from one part to the second arrival? And in order to get that information, you can easily subtract this number from the previous one, and you will get those inter-arrival times. Okay, so this is data from the real system. So, for example, if we get this 27, it's just 104 minus 77, and you will get this number, 27.9. So let's say we have the 23 inter-arrival times for this process. So we observed this for almost 600 minutes. And we were able to capture 23 arrivals. And these are the inter-arrival times. So what do we do with this information? So now I want to be able to predict the arrivals of the next parts for this system. And why do I want to do this? I want to be able to plan for my system. Let's say if I have a larger number of parts arriving or the arrivals are shorter, then I know that I'm going to need more people to help me produce these parts. So I might need to hire another person and so on. So what do? We get these interarrival times and we plot that information into a histogram. And you know about histograms. So this is the histogram for that interarrival times. And as you can see, this shape looks familiar. So what we do with the information of the histogram is we have some software packages that allow us to fit a distribution to this data. So for this particular distribution, we were able to fit a normal distribution with a mean of 25.07 and a standard deviation of 1. So this information, this normal distribution with that mean and the standard deviation, is the information that we use to model the interarrival times in our system. And specifically for this model, you can go to this first block and open that block. You'll see that in order to specify the interarrival times for this system, there's a distribution which is normal. It has different parameters, 3 and 1, and it is in minutes. So the interarrival times of this part right now are modeled with a mean of 3 minutes and a standard deviation of 1. My question for you is, what will happen to the system if instead of a normal 3 with standard deviation 1, we use the distribution that we have here, which is a normal with the mean of 25.07 minutes and a standard deviation of 1. Say that again?
Wouldn't it just increase the whole system?
Well, let's assume that we are going to observe the system for the same amount of time. Let's say we're going to observe the system for 4 hours. What will happen to the number of arrivals in that 4-hour time period? That's correct. We're going to have less arrivals because our interarrival times are larger. Instead of having 3 minutes, so by saying 3 minutes, we're saying that every 3 minutes we're going to have an arrival. Now we're saying that we're going to have 25 minutes. So if every 25 minutes we're going to have an arrival. So the number of units that you're going to see in your system is going to be much less. So let's run this one more time. This is with 3 minutes. You see the arrivals. You see the number of, let's focus on the WIP and the total production. So now, let's say after 130 minutes, we have about 22 units. Now let's change this to 25. 25, or what's the number? 25, yes. You see, now you have those operators idle because you only have arrivals every 25 minutes. So if you're a manufacturer, if you're in charge of this production setting, what suggestions can you make? Oh, you need more input, that's correct. And you need less people, that's true. And maybe the operation, the product is not justified because you don't have that big demand for that particular product. So you might consider exploring another type of product, bring a different production setting, or reduce your personnel, and so on. Let me show you another model. Basically, we all use the concepts from probability, not only for the inputs, but also for the output analysis. So let me see There's an example here from the auto industry. So this one in particular looks at the production setting for trucks. And I think it's just for one of the components. So again, this one is more involved. So you have the parts arriving to the manufacturing plant, and you will see them going through the whole system until the final assembly is completed. So again, this involves more people, this involves more machines, and so on. So these models, again, are used a lot in industry, specifically when you have new products and you need to modify your manufacturing setting. Instead of going there and start playing with your real system, you build a model, you try to come up with some modifications to the system, you test your modifications in the model, and then your suggestions or recommendations are implemented once you have run the experiments and you have tested in the computer. Okay? So this also applies to electrical engineers. Instead of looking at systems, simulation models, you look at circuit panels or circuits in particular for your area of application, and you will run the same thing of simulations for those systems. Any other questions? So again, this is very popular and also for research purposes. Most of my research is focusing on how to develop more efficient simulation models, because usually if you have simulations that needs to manage a lot of data and have a lot of detail, it takes a long time for the computers to run. So there's a lot of research being done in how to improve the efficiency of these simulators. In particular, I'm more into the healthcare applications and into the wind farm simulation type of application. So if any of you are interested in learning more about that, let me know. And if you don't have any questions, then we can move to the material for today. So for today, what I have here is the second part of the continuous probability distributions topic. And we already learned about the normal and the uniform distributions. Today we're going to look at 4 different distributions, and in addition to those 2, and we're going to start with the gamma, okay. So if you remember, for your second exam, you are looking at the discrete probability distributions. You also learn about the expected value and the variance of random variables, and the last thing we did was to look at the first 2 distributions that are listed here, the continuous uniform and the normal distribution. Today we're going to look at these gamma, chi-square, beta, log normal, and the y-ball distribution, and we're going to talk about when are those distributions used and why are they important. So to show you the map one more time, you're familiar with the topics that we have covered so far. So we are now into the continuous distribution topic, and we are going to look at these distributions in particular. So the learning objectives are the same as the one we discussed for lecture 10. So we need to understand the assumptions for each of the continuous probability distributions, and we need to know how to select a distribution based on the data that we have. We need to know how to calculate the means and the variances for specific distributions, and the last 2 basically are for the normal. So let's discuss the gamma. So again, the distributions that we are discussing are based on mathematical models, and they're based on the shape of those mathematical models or those functions. And what we are trying to do is to come up with distributions that we can fit the shape of the function into our histograms, and we can model those data points in such a way that we can predict what's going to happen next in our system. So now we're going to look at the gamma and the exponential. So the normal distribution can be used to solve many problems in engineering and science. However, there's still numerous situations that require different type of density functions. Okay, so again, the density functions or our continuous random variables. Two such density functions are the gamma and the exponential distribution. So the exponential distribution is a special case of the gamma. So the exponential distribution is a special case of the gamma, and the exponential gamma distribution play an important role in both the queuing theory and also the reliability theory. So queuing are the models that look at the queues. So there's a lot of models that basically look at the service time of a particular server, and then they can predict how many units the system can process in a specific period of time, and also perform the analysis if you have a single queue, multiple queues, and so on. So there's a lot of work being done in that area. Reliability is mostly related how often do you need to check the system to perform maintenance. Maintenance cost. So you don't want to perform maintenance too often, but you don't want to perform maintenance. You never perform maintenance because you know your system is going to fail at a certain point. So you need to find the best way to perform maintenance to your system. So those are two areas in which the exponential distribution and the gamma become very useful. So the gamma distribution derives its name from the well-known gamma function, which is here. So this is the gamma function. We have the integration of x to the power of alpha minus 1 times the exponential minus x dx. And these are simple properties of the gamma functions. So this gamma function is equals n minus 1 times n minus 2 and so on for a positive integer n, which is the same as having the factorial of n minus 1. These are just properties from the function. For the course, we don't need to know those properties. We're going to look at the gamma from a different perspective. But we need to know that this probability distribution derives from this function. So the continuous random variable x has a gamma distribution with parameters a, alpha, and beta if its density function is given by this function. So we're going to have parameters alpha and beta, and those parameters are going to define our function. I'm going to talk about them in a few minutes. Those parameters are always greater than 0. So alpha and beta, which are here, here, and here, always need to be greater than 0. So this is how the gamma distribution looks like, and from here you can see why it's important to list the value of the parameters. Specifically for the gamma, if you have, for instance, a alpha equals 1 and beta equals 1, this is the shape that the gamma distribution is going to take. But if you change one of those parameters, for example, alpha equals 2 and beta equals 1, then the shape will change to this. And if you change alpha one more time, then it will look like this. So there's a lot of shapes that this distribution can take, which is very good if you're trying to fit your histogram information into a distribution. So the gamma again becomes very useful. Depending on the parameters, it can assume a particular shape. So the mean and the values of the gamma are right here. So you are familiar with the concept of a mean, the expected value. So if you want to compute the expected value of gamma, you need to multiply your two parameters, alpha and beta. And if you want to get the variance, then it's alpha times beta squared. Any questions so far? Okay, so from now on, I'm going to show you the shape of the distributions because, again, you're gathering some data from your process of your real system, and you're trying to fit a model to that data using the histogram. By fitting a model, you're basically looking at the shapes of each one of the distributions, and you're trying to find the best shape that fits the shape of your data. So this is the gamma. The special gamma distribution for which alpha is 1 is called the exponential. So again, the exponential is a special case of the gamma, and if you go look here, when alpha equals 1, this is the shape. So for those of you who are familiar with the shape of e to the power of x, you know it looks something like this. So the exponential distribution has that shape. So the continuous random variable x has an exponential distribution with parameter beta if its PDF is this one. So we're going to have a function in terms of x and beta. Beta is a parameter, and it's going to be 1 over beta times e to the power of minus x over beta for x greater than 0. And beta is always greater than 0. The mean and the variance for the exponential distribution is right here. The mean is going to be given by beta. So beta is the mean. The variance is beta squared. So as I mentioned a few minutes ago, I do research on the reliability of wind turbines. So right now I'm looking at the particular wind farm in the west of Texas, and we are looking at a wind farm with 100 wind turbines, and we are trying to find out the best way to perform maintenance for these wind turbines. Okay, so this is a type of problem that we are starting to look in more detail because it's going to become a very important issue for the country in a few years, because we have a plan of having almost 20% of the energy generated by wind turbines in the next 20 years. So we think that at some point the reliability of these systems is going to be important, and knowing how to perform maintenance to these systems is going to be very important. So suppose that the system contains a certain type of component whose time in years to failure is given by this random variable t. So this is our random variable, and it is the time in years to failure. And t is modeled nicely with the exponential distribution with mean and time to failure, beta equals 5. If 5 of these components are installed in different systems, what is the probability that at least 2 are still functioning or at the end of 8 years? So this question has two components. First component is this part. You want to know what is the probability of these components to last more than 8 years? And we have another part of the question is we are looking at 5 of these components. We are not only focusing on one. We want to know we have 5 components, and what is the probability of having these 5 components lasting more than 8 years. I'm sorry. So the first thing we're going to do is to look at the probability of these components to last more than 8 years. Okay? And we know that that random variable t is modeled nicely using the exponential. So we know that that random variable, after we put the data into a histogram and we fit the information into our data, we saw that the exponential distribution was the best fit. Okay, so we know that exponential is going to model that time to failure nicely. So we want to find out what will be the probability of that component last more than 8 years. So again, we're going to use the exponential. So let me put the exponential PDF here. This is 1 over beta e to the power of minus x over beta and 0. And this is for x greater than 0. And this is elsewhere. So again, t is defined as the time to failure. So we want to find what is the probability of t being greater than 8 years. And we know beta, in this case, equals 5. So to find that probability, what do? You have a PDF, you have your mean, you have your density function. What's next? Correct. You need to integrate to find the probability. So in this case, we go from 8 to infinite. We substitute the value of beta, 1 over 5 e to the minus t divided by 5 dt. And if, let me do the math for you, this is 1 over 5 e to the minus t over 5 divided by 1 minus 1 over 5. And this is evaluated from 8 to infinite. And this is going to be equal to e to the minus 8 over 5, which is 0.2. So the probability of this component last more than 8 years is going to be 20%. Okay? Are we done? Well, we are done with the first part of the question. What is the probability that at least, well, the second portion of the question is the probability of lasting more than 8 years, but we are interested on at least 2 of them lasting more than 8 years. So we know the probability of lasting more than 8 years, and we are interested on having at least this many successes. We know the probability, and we want to know that at least 2 are working after 8 years. Does that remind you about any other probability distribution? At least these many successes. Correct. So we are going to use this probability, 0.2, and we're going to look now at having at least 2 of them being working after 8 years. Okay, so we know the probability, so let x represent the number of components functioning after 8 years. Then using the binomial, we can find the probability of x being greater than or equal to 2, which is going to be equal to the summation from x equals 2 to 5 of the binomial with x, 5, and probability of 0.2. This is going to be equal to 1 minus the summation from x0 to 1 of the binomial with x, 5, and 0.2, which is 1 minus 0.7373, and this is coming from the table, and that probability is 0.2627. So the probability of having at least 2 of them from the 5 working more than 8 years is 26%. Any questions? So here we are combining 2 distributions to answer one question. The exponential is telling you the probability of lasting more than 8 years. Again, it's an interval time. When this failure is going to occur, is it going to occur after 8 years, it's going to occur after 7 years, and so on. And then once we found that probability, now we are interested by knowing that probability of that reliability of the system. We know that we have 5 components. What is the probability of having at least 2 of them working after 8 years? Use the binomial. Any questions? Okay. The exponential distribution has one very important property that you need to remember, and I'm going to explain that property now. So the most important application of the exponential distributions are situations where the Poisson process applies. You remember when you use a Poisson distribution, right? When do you use the Poisson? What is the case? What is the type of random variable? Yes. So you're counting. You have a period of time, and you want to know how many arrivals you're going to have during that time period, right? That's the Poisson. That's the Poisson process. So the exponential distribution is more important when this type of process, when you are analyzing these type of processes. Okay, so in which you have a Poisson random variable, you're looking at the number, let's say you're looking at the bank, and you want to know how many clients are going to arrive during peak hours. So you want to have all your servers there to serve these people. So that's the type of Poisson process. You're going to have these many arrivals arriving in these from 5 to 6, for instance. So that's the number of arrivals. So recall that the Poisson distribution is used to compute the probability of a specific number of events during a particular period of time. In many applications, the time period is the random variable. So instead of looking at the number of arrivals in the time period, say having 10 arrivals per hour, we are now looking at the interarrival of these. Let's say you're looking at a Poisson process and you have time 0 and time 10 minutes, and you have 3 arrivals. And that's your arrival 1, arrival 2, arrival 3, and arrival 4. And this occurs at time 2, time 4, time 7, and time 9. So your random variable for the Poisson process is you have 4 arrivals. But in many applications, the random variable, instead of being the number of occurrences during the time period, it is the actual interarrival time. So instead of looking at those arrivals, we're going to look at how much time in between. So your random variable now is 2, 2, 3, 2, and 1. So instead of looking at the number of arrivals, now we're interested in the time between those arrivals. And that will become your new random variable. So, for example, we might be interested in modeling the time t between arrivals at a congested intersection during rush hour to plan the expansion of the intersection, or to plan for the use of a bridge to justify the investment. Okay? So that's one thing that you can do. What is the relationship to the Poisson process? So an arrival represents the Poisson event, and I believe this is lecture 9. In lecture 9, the Poisson distribution was developed as a single parameter distribution with parameter lambda. Okay, so you remember lambda was this many arrivals per minute, this many arrivals per hour, and so on. Lambda may be interpreted as the mean number of events per unit time. So now consider the random variable described by the time required for the first event to occur. So if you look at this graph, we have, again, time period 0. you have your first arrival happening here after time t. And then you have a second arrival, which is going to be adding the time from A1 to A2. So if you look at the interarrival time, the first interarrival time will be described from here to here. Second interarrival time will be described from here to here. So using the Poisson distribution, we find that the probability of no events occurring in the span up to time t is given by this. So if you want to find the probability of having no events or no arrivals, then you just put x equals 0. And that's what we're trying to show here. So we find the probability of no events occurring in the span of up to time t, which is here. So from 0 to t, there's no arrival. So you will find that probability by looking at the probability of x being equal to 0, no arrivals in that time period. We can now make use of the above and let x be the time to the first Poisson event. Okay, so the probability that the length of time until the first event will exceed x is the same as the probability that no Poisson event will occur. So, having x be equal to 0 means that no events is going to happen in this time period. And when you solve this, this is the expression that you're going to have. It's the exponential minus lambda x. Okay? Probability of x being equal to 0. If you plug 0 here, this is the result. And that's our cumulative for defining no arrivals up to this particular x. So, the cumulative distribution function for x is given by this. So instead of looking at the x greater than x, we look at the complement, then we have 1 minus e to the minus x to find the probability of x being within 0 and x. In order that we might recognize the presence of the exponential distribution, we need to differentiate the cumulative distribution function above to obtain the density. So if you derive this cumulative distribution, you will find that the function that you obtain by doing the derivative of this function is this one. And I can show you that. So, this is going to be equal to e to the minus lambda x times minus lambda, and 0 minus that. This is going to be equal to lambda e to the minus lambda x, which is right here. And which is the density function of the exponential if you substitute and you make lambda equals 1 over beta. So this will be 1 over beta e to the minus x over beta. And if you recall, that function is the exponential. So by looking at the Poisson process, you can show that the interarrival times of the Poisson arrivals follows the exponential distribution, which is a very important concept in probability. Any questions? So the idea again is to show you that if you have a Poisson process, you can show that the interarrival times of that Poisson process always follow an exponential distribution. Notice that the mean of the exponential distribution is the parameter beta, which is the reciprocal of the parameter in the Poisson distribution. The important parameter beta is the mean time between events. Okay? So may equipment breakdown do follow the Poisson process, and thus the exponential distribution does apply. So if we know that the number of failures in your system follow a Poisson, then you can right away know that the interarrival times of those failures will follow an exponential. So here we have another example. Suppose in a large corporate computer network, user logons to the system can be modeled as a Poisson process. So you have a certain number of logons happening within this time period. With a mean of 25 logons per hour, what is the probability that there are no logons in an interval of 6 minutes? And then what is the probability that the time until the next logon is between 2 and 3 minutes? Okay, so again we know the interarrival times can be modeled using the exponential. And we know the exponential distribution looks like this. F equals 1 over beta e minus x beta, and this is for x greater than 0 and 0 elsewhere. We know beta is the mean time between arrivals. And that is the mean of the exponential. But the information we have is 25 logons per hour. So if we're going to use the exponential distribution, that is not what the mean is telling us. The mean is telling us the number of arrivals per hour. What we need is the mean interarrival time to use the exponential. Have any idea how to transform this into mean interarrivals times? You do 1 over that. If you do 1 over that, this becomes 1 hour logon. So you're going to have 1 over 25 minutes or hours, hours between every logon. And using this information, this is going to be equal to 0.04 hour logon. Okay, so the first question is, what is the probability that there are no logons in an interval of 6 minutes? So, how would you state that probability? So you can do this in different ways. One way is to find the probability of having the first arrival after 6 minutes. Okay, so if you show what is the probability that the first arrival occur after 6 minutes, then you know that there will be no arrivals on the first 6 minutes. So we can state that as the probability of x being greater than 6 minutes. But beta is in hours. So we need to be consistent in terms of the units that we are using. So we need to change these 6 minutes into hours. So this is the probability of x being greater than 0.1 hour. 6 minutes in an hour is 0.1 hour. And now we can integrate. So we will go from 0.1 up to infinite. 1 over 0.04 e to the minus x over 0.04 dx. This is going to be equal to the integral from 0.1 to infinite of 25 e to the minus x times 25 dx, and that probability equals 0.04 0.082, which is about 8%. So the probability of having no logons in an interval of 6 minutes is about 8%. Any questions? And this is, it's not easy to see. So I would recommend you to go back and review this. Okay? This is not easy to see. Now let's look at the next questions. What is the probability that the time until the next logon is between 2 and 3 minutes? Okay, so again we are looking at the probability of having the next arrival between these two time periods, 2 and 3. So we can state that probability one more time. 2x3 Can we solve this using our information right now? What do you need to do? Correct. You need to change this to hours. So this is equal to the probability of x being between 0.033 less than x less than 0.05. And this is in hours. So remember, you need to be consistent with your units. Okay? If you want to solve the problem using minutes and having your mean or the interarrival times in hours. Excuse me. So using the same integral but with different limits, we can find that probability 0.05 25e to the minus 25x dx. That will be equal to 0.12. Does this make sense? These two results? Yes, you can do it the other way around. That's correct. It does make sense. This is telling you that you have a very small probability of having your first arrival after 6 minutes. So which means that you're most likely to have your arrival earlier than that. So when you look at the probability of having your arrival between 2 and 3 minutes, you'll see that the probability is going to be higher. Okay, still have a couple of minutes before I pass the exam. So here we have another example. Based on the extensive testing, it is determined that the time y in years before a major repair is required for a certain washing machine is characterized by this function. Can you recognize that function, that PDF? What type of function is that one? The exponential, okay? So I might not tell you this is the exponential distribution. I can show you that function, and you should be able to recognize the exponential from there. Very easy to recognize once you see the exponential function inside the function. Okay, so we have the mean of 4, right, for the exponential. And we want to know what is the probability that the years before a major repair is greater than 6. So I guess this one is straightforward. You have y. You need to know what is the probability of y being greater than 6. And having the function, you just have to set up the limits. You'll go from 6 to infinite. 1 over 4, e to the minus y over 4. dy. And I'm skipping the details for the integration. If you have doubts, let me know. I'll show you how to integrate this. But that probability will be 22%. The next question is, what is the probability that a major repair is required in the first year? How would you state that probability? It's going to be the probability of what? Y less than, greater than, equal to. Okay, here. This equal. Okay, so it's very, very important point. Now that you raise the equal sign in PDF, you are dealing with continuous random variables, and if you do equal, you'll get 0, because the probability of having a value equal to a decimal place is very unlikely. Okay, so when you have continuous random variables, you will not be able to find a probability of something being equal to. I know I mentioned that as an option. I was just trying to see if you were mentioning it. Okay, so again, for continuous random variables, you never find an equal sign in the probability. So the options are less than or greater than. Less than, correct. So the probability of y being less than 1. And you know your function is defined from y greater or equal to 0. So your integration will go from 0 to 1. 1 over 4 e to the minus y over 4 dy. And this is 0.221. Those probabilities are about the same. It's very interesting. Okay, there's one property, and I think I'm gonna wait until next time to explain this property. This is called the memory-less property of the exponential distribution. Anyone has an idea of what that means? Memory-less, have you heard that before? If you have heard that before, please raise your hand. 1 person, 2 person. Okay, so the exponential distribution has this nice property that basically says that whatever happens before the time period that you are looking, it's not going to affect the probability of your next event. Okay? And that's a very nice property. So the conditional probability for the exponential, it's not going to affect the probability of your next event. So we're going to talk about that next time. And now I'm just going to stop here and pass your exams.